Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Good evening and welcome to Contemporary Science Issues and Innovations. Tonight it's our special pleasure to welcome astronomer Arjun Dey of the National Optical Astronomy Observatory in Tucson, Arizona. Arjun Dey's research focus is the formation and evolution of galaxies and their distribution. This year, he's a research fellow at the Radcliffe Institute for Advanced Study, and he's investigating something he'll explain to us tonight: filamentary flows into regions where massive galaxies are forming and the dark matter associated with the distribution of those galaxies. He'll also discuss his efforts to locate the earliest galaxies in the universe and some work that he's doing on dark energy. Dr. Dey received his PhD in astronomy at the University of California, Berkeley in 1994, and then was a postdoctoral fellow at the NOAO and a Hubble postdoctoral fellow at Johns Hopkins University before joining the scientific staff of the National Optical Astronomy Observatory. Today at the NOAO, Dr. Dey is project scientist for the NSF DOE DESI project, that's an acronym, on dark energy, and the contact scientist for Kitt Peak National Observatory. Dr. Dey has served on the National Advisory Council Astrophysics Subcommittee for NASA, and he's an active representative of the astronomy community to federal funding agencies. He's published over hundreds of professional papers, and because he's an excellent communicator, we hope he will eventually write something about large-scale structures in the universe for the general public. We are very pleased to welcome Dr. Arjun Dey tonight. Welcome.
Thank you. It's a pleasure to be here.
And we'll start right in. This is a big universe, a lot to cover here. Now, you cover this evolution of galaxies, so I need to start out with the term I think that we hear and we don't necessarily understand, which is large-scale structures. Could you tell us what are large-scale structures in the universe?
Well, galaxies are not distributed smoothly and homogeneously in the universe. I mean, they are on very large scales. But if you look at where they lie in the universe, they're structures, they form structures that are highly non-homogeneous. They're not uniform. They form, you see them in clumps, which are clusters. You see them distributed in filamentary structures. And so this entire web-like distribution of galaxies is what we sort of generically call large-scale structure.
Okay.
So these are very, very large structures where light would take hundreds of millions of years to cross.
Okay, but when you talk about large-scale structures, you're talking mainly about galaxies. That's the
galaxies trace the distribution of the large-scale structure, but the structures themselves are defined mainly by the distribution of dark matter that pervades the universe.
Okay.
So the dark matter itself is quite clumpy and not distributed homogeneously, and galaxies form in regions where there's more dark matter. And so as a result, we tend to have these very non-homogeneous distributions of material in the universe, and some of these persist for the entire age of the universe, so they can give us clues as to how the universe evolved with time and how galaxies formed in the context of this large-scale structure.
Right. Now, we've understood that the distribution of the evolution of galaxies has something to do with the quantum fluctuations at the very beginning. Is that what you base that on? In other words, there was a seeding of the universe.
Right, that's our current paradigm in which we understand how galaxy evolution and structure formation took place. the idea is that after the Big Bang, tiny fluctuations that existed in the universe on the quantum scale were amplified during inflation and create a very small ripple, a bunch of little small ripples in the universe, where the differences in density from place to place are 1 part in 10 to the 4, 1 part in 10,000. So they're very, very tiny.
Yeah.
And gravity then takes over and grows these little fluctuations into denser and denser structures until, you know, we end up with you and me here sitting around this table.
Exactly, and some massive galaxies
Right,
floating
exactly.
around too. Before we leave this, what is the large-scale structure, the first term anybody ever hears on this from the outside is usually the Great Wall. And so that's kind of an icon. What is the Great Wall? Was it the first thing ever seen, or?
It was. There was a very pioneering survey that was done for understanding the distribution of galaxies, measuring their distances and placing them in a universal context. And that was carried out here at Harvard at the Smithsonian, you know, at the Center for Astrophysics, which is a combination of the Harvard Astronomy Department and the Smithsonian Astrophysical Observatory. And people went out and measured distances to a whole bunch of galaxies. These were all very nearby, things that, well, in our backyard, if you will, that included structures like the Coma cluster of galaxies and so on. And what they saw was this incredibly inhomogeneous structure, and they found one very large one, which was then termed the Great Wall. So, you know, subsequent surveys have expanded our view of this universe from our backyard to nearly 7 billion years out in time. And so we're getting a bigger and bigger understanding, or a wider understanding, if you will, of the kinds of structures that occupy the universe.
Right, so it didn't stop with a Great Wall.
No, that was the beginning, I think.
But it seems like that wasn't so long ago. I think that was found in like the 1980s.
Yes, exactly.
I wasn't sure. I knew it was CFA, but that is amazing. Okay, let's talk about
part of it is the story of technology, because in those days you really had to go out and measure galaxy distances or their recession velocities one by one, and it took a long time.
I see.
And now we have these very powerful spectrographs, and at the end of this we'll talk about an even more powerful spectrograph that can measure thousands of these at a single shot.
Right.
And that's really revolutionized our ability to do these kinds of explorations of the universe.
In a very short time. That's really amazing.
Yes, exactly.
But we'll definitely talk about that. Well, let's go back to massive if we can for a minute. So what do we mean by massive? I know this is really, really big.
Yes, it's a really bad term because everything has mass. And galaxies can stretch from being very small, dwarf-like things like the Magellanic Clouds, which are our nearest neighbor, very small galaxies, to things that are very, very large, much, much larger than the Milky Way. And the largest galaxies can be 10, maybe more, times the mass of the Milky Way. And they come in different shapes. There are things that are spiral galaxies, like our Milky Way, and things that are like the big galaxies that sit in the center of nearby clusters that are very large elliptical galaxies, and those tend to be the most massive galaxies in the universe. So those could have, as many as 10 to the 12 suns worth of mass inside them, and our Milky Way is more like 10 to the 10 and a half or so.
Yeah, right. But there's no, in principle, is there any endpoint, any upper limit on massiveness, and I meant size of these galaxies, of these huge galaxies, because they're like little galaxies, medium.
Right. Well, galaxies grow with time.
Okay.
And the most massive galaxies have suffered a lot of mergers or eaten other galaxies. I'm anthropomorphizing it, but have merged with other galaxies to grow in size. And so you can imagine with time, some of these really big galaxies that sit in clusters will grow larger with time. But the largest and most massive ones are also extremely rare in the universe. And so as a result, we don't find galaxies that are very much more than a few tens of the weight of the Milky Way in the local universe, at least.
Okay. And the universe is very big. It stretches back. You're going back to earlier and earlier times. Is there any location in terms of time where you would find these supermassive galaxies, or it's an ongoing thing close to us and way back in time?
Well, the way the universe and structure evolves in the universe is what we term hierarchical. So in other words, the most dense parts of the universe, the largest fluctuations in the universe that were seeded at these early times, grow more rapidly. And as time goes on, smaller fluctuations grow to the point where they can become galaxies as well. So the evolution proceeds hierarchically in the sense that the largest objects tend to collapse first and grow, have a longer time as a result to grow, whereas even now there are galaxies forming, but they tend to be the dwarf galaxies, and smaller things subsist to this present time.
Okay, then in terms of the formation of these, you sort of alluded to it, but is there any kind of special force that causes this? You talked about, being gobbled up by your friends and neighbors, and the distances and everything. Is there any particular force that causes the massive galaxies? It's just if you're close to somebody.
Gravity dominates the way in which these structures evolve.
Right.
And it's really the gravity not just of the galaxies that we see, but really the dark matter that dominates how these galaxies evolve. So in denser regions where there are more galaxies and more dark matter, that drives the evolution. In less dense regions, there's less dark matter and less galaxies, and so fewer galaxies form there.
Okay, then we have this mess of galaxies, and the universe is expanding all the time, and we have this web-like structure. What is that web-like structure? What are the filaments? What is pulling, what's that stuff that we see, those little lines? Well, are they just drawing those things there?
No, well, the unusual thing about the galaxy distribution is that it has all these very strange structures, that these filamentary, like it forms itself into these filamentary like structures.
Yeah.
We assume that the reason that those structures exist is because the dark matter is distributed in that manner. Now we don't actually see the dark matter directly, and that's one of the great puzzles of modern astrophysics, is understanding what the dark matter is made of. But we infer its presence from the gravity that we, from studying the motions of galaxies in various regions. So for example, if you look at our own Milky Way galaxy, it's spinning around quite happily. In a very analogous way in which we can infer the mass of the sun by studying the orbits of the planets, we can also infer the mass of the Milky Way by looking at the way in which the stars go around the center of the Milky Way. And we find that the amount of mass it requires is way more than the stars that we actually see. So if you go up to the cluster scale and you look now not at single galaxies, but the way galaxies move within the cluster, those velocities are sort of tell us that there's a lot of mass in the cluster that we just don't see. And so we call that dark matter only because we don't really understand what it is. And it's one of the excitements and one of the embarrassments, I guess, of modern astrophysics.
Right. I started to ask about the filaments, the stuff that's tying these things together. In terms of the filaments, is this anything? We see these lines. Are these gas lines or something?
Well, we do think that there's gas in the filaments, but the primary material in the filaments we think is dark matter. So sorry, I didn't finish that thought, but you can imagine the universe, being sort of an ocean of dark matter, some parts being more dense than others, and in the regions where the density is higher, that's where the galaxies tend to form. So the whole universe might be sort of sponge-like, where there are empty parts and denser parts where the sponge material would be, but it's not, a sharp distinction between empty and all of a sudden I have my piece of my sponge. It's sort of a continuum, and it's only where the density goes up above a certain point where you see the galaxies forming. So if you can think, when we imagine the universe having these filamentary structures and so on, if we could see the emission that dark matter produces, we might see it all glowing in this manner.
Yes.
Now, these filaments are also filled, we think, with diffuse gas that is accreted as a in fact, that gas somehow essentially forms the galaxies. It might be the stuff that the galaxies have formed from, but that also follows the dark matter distribution, and it's brought in there purely by gravity. But beyond that, we know very little about this because it's the temperatures of the gas in these regions and so on make it very hard for us to study it directly. But there are instruments that we are now constructing that we hope over the next few years will give us glimpses of this diffuse emission.
It's impressive how fast they're going, actually, that, in terms of what they're able to see. It seems like every year there's a big jump, but anyway.
Right, well, I mean, it's the history of astrophysics that it's been driven by technology, right? From the time that Galileo was able to get his hands on the telescope and use it.
But just in recent years, it's pretty staggering, in the last, I don't know, even 40 maybe.
Yes.
It's just staggering. Okay, so I want to get one more thing straight, and then we go to the dark matter. We are usually given an image of this big web with the massive distribution, the distribution of the massive galaxies, as having voids, and you're talking here about really it's a continuum. Essentially, I think we have thought of that as, there's these huge empty places. What causes that? But you're really not sure that they're so empty. Is that it? Or you don't think that they are? We
don't think that they are. I mean, we do see, when we look at the galaxy distribution locally, we see things that live inside what we would call voids. They just tend to be very low density environments. And then there are other regions where there's stuff, and it may be a higher density environment, and it's there are this filamentary structure probably has a whole range of environments that in which galaxies form. And it's really tracing that and understanding why galaxy formation is different in different regions. That's one of the challenges of astrophysics. For example, if we look at clusters today, we find that dense clusters tend to have old galaxies that have completed most of their star formation. They tend not to have much ongoing star formation. There are spiral galaxies, but they don't have a lot of gas in them. Whereas if we look in what we call the field, in other words, things that are not in dense clusters, and we see gas-rich galaxies. We don't see as many red and dead elliptical galaxies. And it's a puzzle as to why that's the case. Did stuff in clusters evolve more quickly? If so, why? What are the physical processes that drove that? Did the stuff in filaments evolve differently? Why? It's a complicated problem, and we're only just beginning to understand these environmental issues.
That's very interesting. If you talk to an astrophysicist, the astrophysicist always has a whole pile of questions. In a lot of the popular literature, it's all sewed up. So there are many of these things, like the Big Bang, the inflation, and all that. And we were talking about the gravity waves earlier, that there's still a lot of questions. So if you're working with it, you have more questions.
It's a great time to be in astrophysics.
I think it's fantastic. It must be very exciting.
I mean, there's only 4% of the universe that we actually can observe and know about, and the rest of it is just completely mysterious to us.
Would you take us to that now, as a matter of fact, to just restate that for us? And let's talk about the dark matter. You've mentioned it several times here, but this may be is really interesting information that this is the driving force. So, in terms of what is baryonic matter? How much is baryonic matter in the universe?
So the stuff that we know about, the stuff that you're made out of, and I am, and the table, and our audience, and everybody else, is made up of atoms, and which are made up of protons and neutrons and electrons and so on. It's stuff that we can measure in our lab, and we know what it is. And what's quite remarkable to me still is that the properties of the matter that we see today appear to be the same across time. As far back as we can look in the universe, we see atoms radiating pretty much the way they do in our laboratory, and there's no reason why that should ever have happened, but I guess that's the miracle of physics, right? However, if you take all the energy that's associated with that material, it's about 4% of what we think exists in our present-day universe. A remaining 26-25% is dark matter, which is stuff that we think behaves like normal matter. It has gravity, it attracts things, and so we sort of understand its properties, although we don't know what it is. And then there's the remaining 70%, which is some mysterious, even more mysterious thing that we refer to as dark energy, which seems to have the opposite effect that matter has. So, if you build an Earth out of rocks, it'll attract stuff because it has gravity. And if you do the same with dark matter, it'll also behave the same way. But dark energy seems to be repulsive. It has a repulsive gravitational effect. And it's really, that's our current paradigm, that these are the constituents of the universe, but we don't really understand these things very well at all. Or at least I personally do not.
Well, everybody says that who's honest. That's I say, if you walk up to an astrophysicist and ask about it, that's what they will say.
Right.
But there's a great deal of popular literature out there that, or popular programs and so on, that makes it sound like a done deal. We sort of understand this and stuff. But what you're saying is no way. So,
in fact, we need people with clever ideas to come in.
Well,
and solve
it's true, but many people, even in physics, will say nobody's got a clue what dark energy is. Forget it. But it's scary stuff that we can't account for most of what is out there. But I want to just make sure that we understand this one thing that you mentioned, that the dark matter has an awful lot to do with this distribution of the massive galaxies. So, and it's very spotty. Then is that it? It's not smoothly. We always think of the elementary gases as being more or less spread out.
Oh, I don't know. It may well be quite smooth.
Oh, you think?
The galaxies may form at sort of little peaks, if you will.
Okay.
I sort of think of it like when you're beating the egg whites to make something, and they get hard, and you see little hard peaks, right? But there is stuff everywhere, and perhaps the galaxies only form at those little peaks. And that's the only part we see, but there is all this other stuff everywhere else which we're not actually seeing. And it could be quite smooth. It doesn't have to be so clumpy as to be disjointed.
Right. Well, in terms of the evolution of the universe then, and we want to talk specifically about dark energy and dark matter, because that's a lot of what you do, then in terms of the universe, the evolution of the universe, one of the things that we've heard, whether it's myth or not, is that in the early days, I believe it was dark matter, and now it is dark energy. In other words, that one has overtaken the other at some point and suddenly is causing this part of this expansion. Is this something?
I think what you're referring to is the fact that the energy density of the universe was dominated in the past by baryonic and dark matter.
Right.
And since the last 8 billion years, which is about half the age of the universe, we've basically started to see the effects of dark energy, and it's become stronger and stronger.
Yes. Okay.
I want to emphasize that that's our current paradigm. That's the way in which we understand these things.
Could change in 2 weeks.
Probably not in 2 weeks, but our current the way in which we understand gravity is based on Einstein's theory of gravity, and we, that's our. There's nothing that tells us that it's wrong at the present. However, there are people who've been thinking of, do we have to find these new constituents of the universe, or is it just that we need to find a new theory of gravity that accounts for these things in a more natural way? And it's the minority that are working currently on modified theories of gravity, but it's very hard to predict how things might pan out in the future based on observations and studies that will go on.
Right.
And you have to follow the data, whatever it tells you.
Right. So presently, the paradigm is that the one is dominant at one stage of the early stage, and then dark energy is now dominant.
It's becoming much more dominant now.
Right. Okay. And that may change the distribution of the galaxies.
It will. It'll keep the universe expanding forever.
Yes. Okay.
Into nothingness.
Okay. So then we have an understanding of sort of the evolution of the universe now, and you're assuming that it's going to keep on going like this until it just sort of fades out or something. Okay. Since you've worked directly on dark matter and dark energy, can you tell us about what your work has been in those direction?
Well, I'm hardly an expert on either topic, but I've been involved in a project that we're trying to get started called DESI, which stands for the Dark Energy Spectroscopic Instrument. And the idea is to take one of the old and venerable telescopes on Kitt Peak, which is run by the Kitt Peak National Observatory, or the National Optical Astronomy Observatory, and refurbish it with a new instrument that will sort of revolutionize our ability to map the universe. So the idea is it's a 4-meter telescope, which means that the diameter of the primary mirror is 4 meters. And we want to put a spectrograph on top that can take spectra, or measure distances, if you will, of 5,000 galaxies over a 3-degree field of view at one time. And the goal is to use this instrument to map the local, to essentially study the way in which the universe expanded over the last 8 billion years. And we're going to do that by measuring distances to something like 20 million galaxies in the universe. So it'll be an amazing map of what our universe looks like from our little blue dot perspective.
I should say.
And so through time, we'll be able to see how the distribution of galaxies changed and use that information to infer how the expansion of the universe caused that distribution to change. So it's a way of essentially constraining the geometry and the changing geometry of the universe over time.
That's gorgeous, but can I ask very quickly in here too, just as a kind of review for people, in terms of looking at this kind of a scale, as you're looking at a very big scale now, does that make it more difficult to evaluate the distances? In other words, going back as opposed to your little.
Well, there's an amazing phenomenon that took place in the early universe. Essentially, when the universe was very young, material was fairly tightly bound. The light and matter were coupled. So if something moved, the light had to sort of go with it. So essentially, they were all coupled together. And at some point in the universe, after it was about 380,000 years ago, protons and electrons combined, and the light could sort of stream freely. And at that point, certain patterns were imprinted in the universe, certain patterns of density. And the galaxies formed in those patterns, and that pattern can still be seen in time. So it's almost like a fixed scale in the universe. It's like if I took your pen and I put it at a certain distance from you, and you measured the angle and you knew the size of the pen, you could tell how far the pen was. And if I put it at the end of the room, well, the angle would be a lot smaller, but because you knew the size of the pen, you could still tell me how far away it is. It's just a little geometry problem. So the same way, because we know the scale of these ripples in the early universe, and we can see these ripples in the distribution of galaxies, through cosmic time, we can tell essentially how far away all those galaxies are at all those times, and that gives us a direct measure of how the universal expansion took place.
So it's a pretty accurate
it's a remarkably accurate system to use.
That is quite amazing, because that's a lot of distance.
And gravity messes it up towards the local times, but it's still we can still
amazing.
Extract it, and we've been able to do that with other surveys.
Okay. Well, then you're also working on dark energy also, right? And so the dark matter is a part of your work, and then...
So this problem of trying to study how the universe expanded is one of the few ways we think we can get a handle on dark energy, because we really don't know what it is, and there are many theories. But our hope is that if we can understand the way in which the universe evolved, perhaps that gives us clues as to how the dark energy began to affect the universe, and maybe then infer properties of dark energy. But at this stage, we're really taking baby steps into trying to understand this. We don't have any other observational way of getting data on this strange force.
Yeah.
The energies that you require in order to really recreate the conditions in which you might see this sort of physics are sort of beyond our accelerators, our lab experiments essentially. And so we have to use sort of the universe as our accelerator to try and understand these problems.
Is this a situation where an accelerator, a super, whatever, would succeed the Large Hadron Collider, that it would never be able to give you the answer to this?
Lifetime, I
right,
think
right. It's really, really, really big, huh? Or whether that could provide that answer. What is it?
I don't want to rule out what things like the LHC and so on can constrain, and there are other ways of getting handles on the conditions in the early universe that may have given rise to something that would manifest itself as dark energy today. But currently, the only way to measure how the universe expanded over the last 8 billion years is to actually go out and try and study it and try and measure it directly. And for that, the telescope is the only laboratory tool that we really have in order to do that.
Okay, so it's not a matter of like a new physics or something like that to try. Everybody seems just totally bewildered by dark energy, and there just aren't any answers. Dark matter, maybe they'll get a grip in time, but that's a very huge amount of the universe that is,
the energy density is high. The dark matter, there are theories that predict certain kinds of radiation, depending on the particle that you predict makes up the dark energy, the dark matter. Certain kinds of dark matter have certain kinds of radiation that they emit when dark matter and anti-dark matter particles meet each other and annihilate. And there are experiments to try and see this radiation. But we still haven't detected the particle. There's a lot of uncertainty in what the mass of the particle is, and so these are all experiments that I hope will be successful. But they've had, it's still a mystery at the moment as to exactly what it is.
It seems as though people are there are many different, I don't know about many, but there are quite a few different approaches to trying to solve this big mystery, and nobody.
That's great,
yes,
right? I mean, it's very hard. If we were all doing the exact same thing to try and solve the problem, then we're not going to get the right answer.
Right. Well, I can just see that this would be a very motivating thing because it's a very exciting thing, but it does seem it's always out of reach, like some kind of, I don't know whether it's conceptual or what, something is missing to try to determine what it is. You said that you use telescopes to do this. I'd like to just get in a little bit about different kinds of telescopes. Now, you work primarily with the optical telescope, and can you give us an idea of what do these do as opposed to, say, radio telescopes and so on? There are these varieties of things. Are these complementary?
They are extremely complementary.
Okay.
Electromagnetic radiation, so atoms radiate in all kinds of different ways, and different physical processes produce different kinds of radiation. They can produce radio waves or millimeter waves or optical waves, etc., X-rays. Certain kinds of radiation don't penetrate the protective layers of our atmosphere, and so to study those we have to go above the atmosphere, and so those are typically things like ultraviolet, X-rays, gamma rays, infrared radiation. Some of it doesn't penetrate our atmosphere, and we have to go above our atmosphere in order to study it. All of these usually give us complementary or unique information in some cases about certain kinds of problems. For example, atoms mostly radiate at ultraviolet and optical wavelengths, and we can measure that from using optical telescopes. Hydrogen, which is the most abundant material in the universe, has a transition in its ground state, and basically it has a proton, an electron, and the electron spin can either be parallel or anti-parallel to the proton, and that little flip produces radiation at about 21 centimeters. Very long. What is that? Just 9 inches, something like that. A big wave that enters our atmosphere as radio waves and is detected by radio telescopes, and it's critical for our ability to study the universe. molecules like carbon monoxide, methane, etc., they all tend to produce lines that are at millimeter or shorter wavelengths, and so you need telescopes there. And the technology is different for each of these different wave bands. And so it's important to be able to study celestial radiation at all these different wavelengths. At certain radio wavelengths, it's getting harder and harder because we all have cell phones. Well, I don't yet, actually, but everybody else has cell phones. And those tend to, that forms a background or a foreground, if you will, of noise that interferes with some of these kinds of detections.
Right.
So certain kinds of experiments have to move to very remote areas like the Western Australian desert, etc., to really make sensitive, perhaps in the future, the far side of the moon, in order to make these kinds of sensitive measurements. But the optical is, ever since we've been able to understand, it's wavelengths at which we see, and therefore we have a long history of being able to observe the universe through it. And it gives us a lot of information on atoms across time. And so it's a very it will remain a powerful tool by which we study the universe well into the future.
Right, but all of these go sort of together to make a collective picture down the line here.
Right, I would not want to have to pick to choose.
Yes, especially with this advanced technology that seems to be developing by the week. It's so hard to keep up. What's your favorite area in your research? What's the thing that has been most exciting? Was it the...
Wow, there are so many things. I was going to say
the discovery of this very, 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 very early galaxy a while
That was
back.
fun. It's always fun to go to a telescope and discover something that nobody else has seen
I bet
before.
that woke everybody up.
The excitement of discovery is, I think, what drives most scientists in their research, and they happen. Rarely, but in astronomy they tend to happen every time you go to the telescope at some level, because the universe is a big place.
Yes.
And if you look carefully, you're bound to find something interesting.
Yeah.
The discovery of very distant galaxies has proceeded a lot since 1998 or whatever it was that we broke the redshift record.
Tell us about that, though. Okay, so you found, I think
it was actually purely by accident. We were trying to study galaxies in the early universe, and we just happened the light of a galaxy that was at what we called it a redshift greater than 5. So basically something seen within the first billion years or so of the history of the universe. Just happened to be on our spectroscopic slit, and we detected it, and we had looked at enough we had been trying to find these things for long enough that we recognized
these remote galaxies.
Yes, exactly. We recognized it the moment we saw it. So that was very exciting, but it was really, we just happened to be at the right place at the right time.
Modest
it opened. No, it's really true. I think
it was an accident.
It wasn't. I always like to think of it not as a discovery that we made, but it was really a discovery that was made by the telescope and the technology. We had a telescope that was 10 meters in diameter. It was the Keck telescope. It was the largest instrument on the planet at the time, and it revolutionized our ability to see the early universe. And there are plans in the offing now the James Webb Space Telescope will hopefully launch in a few years. But beyond that, there are plans by 2 different consortia to build 20 and 30 meter class telescopes, which will further increase our ability to study the early universe. And that's how discoveries are made. And they open up fields that we didn't know existed and make us focus on things that we didn't think we should be focused on.
Right, it's amazing. What a fascinating area. Is there anything else of your work that you've particularly been thrilled by?
Well, recently I've been studying the formation of, I've been studying regions where we think massive galaxies are forming. And these are regions that, funnily enough, in the scientific literature are known as blobs. They tend to be very large, diffuse nebulae. They're gas clouds that are hundreds of thousands of light years across. And so the entire Milky Way plus Andromeda plus many of our neighbors might have all formed in a region like this.
I see.
And they're very rare because you don't often see big regions of gas just glowing because they are forming stars. And as a result, it's been hard to find them, but they appear to be laboratories in which galaxy formation is taking place. So you can go and take pictures of them and study their properties, and you can see little tiny galaxies inside them. And that part has been very exciting because that's been new and different, and has given us a different insight into the process of galaxy formation.
So this is a bunch of galaxies actually forming out of more or less one cloud, but
exactly.
Rather large cloud, and that is different from what we normally hear. We usually think cloud and it collapses and you makes a galaxy and then a cloud and so on. But so this is
kind
huge.
of like in our galaxy, when we look at star forming regions, we see big molecular clouds, and we see lots of stars forming over here, and perhaps an older generation that formed before it, and so on. And I think we're beginning to see this process analogously, but on a very large scale. Yes.
That's very interesting.
So that's been fun.
I bet. Okay. Is there anything else you'd like to tell us before I turn you over to questions from the audience?
No, keep funding science.
There is an urgent need to fund science. And so can you tell us what you do in terms of representing the astronomy
Well, I can,
field?
The organization I work for, the National Optical Astronomy Observatory, is operated by a consortium of universities on behalf of the NSF, of the National Science Foundation. So the National Science Foundation has an astronomy division, which sits inside math and physical sciences. And it provides some money for facilities, which are like the ones that we operate. And it also provides grant money to fund research by private individuals. The facilities are a very interesting concept because they were set up, I want to say in the 60s, because of a desire to democratize research in this country.
And your organization is especially known for that.
Right, and so they set up both the National Radio Astronomy Observatory and the National Optical Astronomy Observatory. And the reason was that they wanted to provide world-class facilities where anyone at any U.S. university, if they had a smart idea, could write a proposal, have it be peer-reviewed, and get access to these facilities.
Which are hard to get access to, correct?
Exactly. And as federal funding has decreased, this kind of access has decreased. So unfortunately, while I've used Keck Observatory for many years and I still continue to do it, it's largely a privately funded observatory that belongs primarily to Caltech and the University of California system. And there's a portion that's funded by NASA, which is a slice that is publicly available. All our telescopes are completely publicly available, but because of reduced funding, that becomes harder. So one tends to have either their own telescopes in their backyard or some other way of doing science. It's not so much the access, because I think there are many universities that have sources of funding or their own observatories, but it's really an overall approach on how we want to think of science in this country, whether it's a completely unfettered, search for knowledge, or whether it really has to be directed by certain funding agencies. And I think that's really a debate. This was discussed, I guess, in a New York Times article recently on what the right paths are for funding science. And concern about a lot of private money. Right, and I think, like everything else in the United States, this is a grand experiment, which is at the moment going through a decrease in public support. But, we'll see how it evolves. Right, but we appreciate your efforts to get out there. I would say we need more information in the public domain about this, that in general the public does not get a lot of information about how this stuff is funded, and that scientists spend a lot of time with their begging bowls, and it's not a lot of time devoted to that rather than to the, it takes away from the research. So, and also that maybe in the public we are not given a lot of information about where a lot of money goes that could be going to science. So in any case, we appreciate your efforts in that regard. I am now going to turn you over to the audience because I know people would like to ask questions. And before we close, I would say thank you very much. It was really fun.